Hello students, this is Mr. Allen, and today we are going to look at section 7.7, which is on indeterminate forms and something called L'Hopital's rule. Our objectives today are to recognize limits that produce indeterminate forms and to be able to apply L'Hopital's rule to evaluate limits. So it's interesting, we started off the AB curriculum with limits, then we went to derivatives, and then we went to integrals, and now we're coming back to this L'Hopital's rule, which is involving limits. So first, let's be able to recognize some indeterminate forms. So this is a very important slide. This isn't all the indeterminate forms, but probably the two most common, and those are 0 divided by 0 and infinity divided by infinity. And they're called indeterminate forms because you can't, if you get a limit that looks like one of those things, it literally could be anything. It could be 0 for the limit, it could be 10 for the limit, it could be a half for a limit, it could be D and E. So 0 over 0 is not 0. It could be 0, but it most likely is not. It could be anything. So for example, let's look at a couple of examples down here. So in this particular limit, the limit of 2x squared minus 2 over x plus 1 as x goes to -1, if you plug -1 in there directly, you will get 0 over 0. So what is 0 over 0? Well, in this case, it turns out to be -4. And the way we would have done that all the way back in chapter 1 is we would have found the common factor of x plus 1 in the numerator and the denominator, cancel that out. Now we can do a direct substitution with the -1 here, and you'll get an answer of -4. Now let me remind you that if you put -1 in over here, you will get 2 minus 2 over -1 plus 1, which is 0 over 0. So in this case, 0 over 0 actually turns out to be -4. Here's another example, infinity divided by infinity. If we do the limit on the left and directly substitute infinity into that, you will get infinity over infinity. Well, in this particular case, what we would have done is we would have divided by x squared on the numerator and the denominator. And then, of course, the right-hand terms go to 0, so you're left with 3 over 2. So that is what the value of the limit is. It's 3 over 2. So those were the algebraic techniques that we used all the way back in chapter 1. So this is actually kind of a good review of chapter 1. The problem is sometimes you can't use these techniques to figure out what the limit is. So consider the limit here. If you plug 0 into this, you will get e to the 0 minus 1. If I did a direct substitution, e to the 0 minus 1, which is, of course, going to be 0 over 0. This is an indeterminate form. The problem is you have no way to simplify this guy. You are kind of just in trouble. So what we can do is, again, we can do a little bit of algebra to clean things up. So this is a little bit more advanced form of factoring. So we still get a 2, so that's good. So technically, I could give you this all the way back in chapter 1. However, not all indeterminate forms can be evaluated by algebraic manipulation. So consider this limit. Here we literally cannot do anything. Now you can factor the top. The top would factor to e to the x plus 1 times e to the x minus 1. The problem is nothing on the top is going to cancel with that x. By the way, if we did a direct substitution here, you get 0 over 0. So we could rewrite the expression in this way. This produces another indeterminate form, and this particular indeterminate form is infinity minus infinity, which, by the way, you might think that's 0, but that is not necessarily the case. If we look at the graph using technology, and we're talking about the curve e to the 2x minus 1 over x, by inspection, you can see that that curve appears to go through the value 2. If we look at the table of values close to x equals 0. That is indeed the limit. But how are we going to get that limit if this was a no calculator part of the test? So I could have given you this problem back in chapter 1, but it would have been on the technology part of the test. So that's why we need this thing called L'Hopital's rule. Okay, so let's just go ahead and get to and the general idea is this. If I'm trying to find the limit of a quotient, I can actually use the derivatives of the functions to figure that out. So here it is. This is the most important slide besides knowing the indeterminate forms. This is called L'Hopital's rule. It says let f and g be functions that are differentiable on the open interval except for possibly at c. We want to make sure that g prime is not equal to 0 because we don't want to have any division by 0. If the limit of f divided by g of x is an indeterminate form, then what we can see is that here's the big idea. The limit of f of x over g of x as x approaches c is equal to the derivative of f divided by the derivative of g. So this can help us figure out what those indeterminate forms are. Now, let me make sure I make a note. This is not the quotient rule. And I hate to even bring this up right now. But if you remember the quotient rule, low d high minus high d low over low low, this is not that. If we have a quotient of functions, we're using L'Hopital's rule, then we do the derivative of the top function over the derivative of the bottom function, and we do that limit. This is not the quotient rule for differentiation. Let's look at an example. Now, I'm going to do this kind of the wrong way first. So if I did, and by the way, this is the same problem we looked at. We already know the answer to this. We know that the answer is 2. But if I did a direct substitution, we would get e to the 0 minus 1 over 0, which is 0 over 0. That's an indeterminate form. And it's the indeterminate form 0 over 0. Now, something that I encourage you to do on the AP exam is don't show your work like this. And I know I just did that. But what you want to do is you want to show that the numerator's limit goes to 0 and the denominator's limit goes to 0 separately. Okay? So show that they go separately because this right here, this means nothing. So just we're using the quotient rule for limits. So we're doing the limit of the numerator divided by the limit of the denominator. So that is 0 equals, the limit as x goes to 0, the numerator is 0. The limit of x as x goes to 0 is also 0. So now what we're going to do is we're going to apply L'Hopital's rule. So L'Hopital's rule, which is right here, which says I can do the derivative of the numerator and the derivative of the denominator limit. So that's what we're going to do. The limit of the numerator, we got to use the chain rule, which is going to be 2e to the 2x. The derivative of 1 is 0. The derivative of x is just 1. In other words, we're literally just talking about the limit as x goes to 0 of 2e to the 2x. So now we can just do a direct substitution. So that's going to give us the limit as x goes to 0 of 2. Oops, I didn't need to write that limit there again. I'm sorry. So that just be to the 0, which is just 2 times 1, which is just 2. Okay, so that is an example of L'Hopital's rule. If I've given you this back in chapter 1 without technology, you would not. There's nothing you could do algebraically to get the answer of 2. Okay, so here is another very important slide. When you are evaluating limits, here are the indeterminate forms that you need to be aware of. We've already talked about these 3 right here. 0 divided by 0 and infinity divided by infinity are the most popular. Another indeterminate form is infinity minus infinity. Also, we have the indeterminate form of 0 times infinity. It seems like 0 times infinity should be 0, but it is also an indeterminate form. 0 to the 0 power is an indeterminate form. 1 to the infinity, which you'd think that's 1. That is an indeterminate. These are all indeterminate forms. So there are 1, 2, 3, 4, 5, 6, 7. There are 7 indeterminate forms. Now we do have some determinate forms. Determinate means we do know the answer. So for example, if I have a limit that turns out to be infinity plus infinity, that's just infinity. That kind of makes sense. Similarly, negative infinity minus infinity is negative infinity. So if I go negative infinity and negative infinity more, that's still negative infinity. 0 to the infinity does go to 0. Now notice that that's a little bit different than this guy up here. 1 to infinity, that one's indeterminate. And 0 to the negative infinity, that one is infinity. Okay. Final comment on this. All of these other forms over here, all of these guys over here, can be reduced to these two here. Okay, now they require some sophistication, but they can all be reduced back to that. I shouldn't say all, but any of the ones you're going to basically deal with can be reduced back to that in this class, because you're going to need to use L'Hopital's rule. They're not going to give you one that you can't do without L'Hopital's rule. All right, so for instance, the following application of L'Hopital's rule is incorrect. Now notice what we wrote here. It says the limit as x goes to 0 of e to the x over x equals the limit of e to the x over 1 equals 1. This is the incorrect use of L'Hopital's rule. The reason that this is incorrect is that the limit of the denominator is 0. The limit of the numerator is 1. In other words, if you do a direct substitution into this, you get e to the 0 over and then x. That guy is just going to be 0. This is 1 over 0. That is not equal to 1. Remember, in order for you to use L'Hopital's rule, it has to be 0 over 0 or infinity over infinity. So be very careful about how you do this. Okay, so this one is incorrect. Let me go back to that L'Hopital rule page here. Sorry. Provided that the limit on the right exists, the result applies to, and then these are the indeterminate forms: infinity over infinity, negative infinity over infinity, infinity over negative infinity. Oh, and 0 over 0. Don't forget about that one either. Okay. 0 over 0. It has to be one of those. It does not apply in this particular case because you have 1 over 0. That's not a L'Hopital rule problem. All right, last example. So I wanted to do one example where we're going to get the indeterminate form of 0 times infinity. So if we did a direct substitution on this particular problem, you are going to get e to the negative infinity times the square root of infinity. Well, this is going to go to, well, let's see here, e to the negative infinity going back that way. That's going to go to 0. And of course, the square root of infinity is infinity. So this is an indeterminate form. This is 0 times infinity. So I'm going to put therefore indeterminate form. Okay. So now what I'm going to do, and the reason I'm doing this one is I just want to show you how you deal with it. So all we're going to do is we're just going to change this to division. That's what we want to do anyways. So I'm going to leave the limit as x goes to infinity. But remember, the square root of x is the same thing as x to the 1/2. And then what is e to the negative x? Well, that's the same thing as taking the e to the x to the denominator. Now, I'm going to show you the work the way I would recommend that you show your work. We can see that the limit as x goes to infinity of x to the 1/2, that is equal to, well, that's equal to infinity. And then the limit as x goes to infinity of e to the x, that is also infinity. So again, we can see that we've got infinity over infinity, which is again an indeterminate form, but now we can go ahead and use our L'Hopital's rule. And so I'll do that in green. So we're going to go to L'Hopital. By the way, you'll hear my former students referring to this as going to the hospital. So we're going to do L'Hopital's rule, which is going to give us the limit as x goes to infinity. We got to do the derivative of the numerator. The derivative of x to the 1/2 would be 1/2 x to the negative 1/2 divided by, and then the derivative of e to the x is e to the x. So I did the derivative of the top function divided by the derivative of the bottom function. So that is going to give me the limit as x goes to infinity of, and I'm going to go ahead and write this now as 1 over 2 square roots of x over e to the x. Now when I do a direct substitution, I'm going to get 0 over infinity, which, by the way, goes to 0. So this limit is 0, and we will stop it there. Thank you.